In most of human history, the night sky has looked calm, finished, almost familiar. But what if that was never the real sky at all? What if it was only the brightest surface of something far deeper, far more active, and far more crowded than anyone could truly see before? Rubin Observatory may soon reveal millions of hidden changes, unseen objects, and patterns buried in the darkness of the southern sky. If this kind of cosmic mystery fascinates, please like the video, subscribe to the channel, and stay for the journey. Above the southern half of Earth, the night sky opens as a layered field of light and darkness. It appears at first as a surface, but it is not a surface at all. It is a direction of view, a deep passage through space, filled at every depth with different kinds of objects and different histories of light. Some points belong to nearby stars within the Milky Way. Some faint smears belong to whole galaxies far beyond it. Some dark lanes are not empty places, but regions where dust stands between the observer and more distant light. Between the brighter markings lie wide areas that seem almost blank. Yet even these quieter parts contain stars too faint for the unaided eye, and galaxies so distant that they gather into a soft background only a sensitive instrument can record. The southern sky is therefore not a ceiling over the world. It is a vast visual record of matter spread through many scales of the universe. For Rubin Observatory, this southern sky is treated not as one picture but as a region to be visited again and again, until its visible contents become more complete than before. Its importance begins with its size. The sky over the southern hemisphere contains rich parts of the Milky Way, nearby satellite galaxies, star clusters, distant galaxy fields, and many regions that have not been followed with the same wide, repeated depth in older surveys. To look outward across that half of the sky is to look across a mixture of local structure and remote structure at once. The nearest and the farthest lights enter the same field together. A star within the home galaxy may shine in front of a galaxy whose light has travelled for billions of years. A cloud of dust may partly veil a dense star field. A dark patch may hide a brighter population beyond it. The southern sky gathers these layers into one visible whole. Seen without instruments, the sky seems orderly. Familiar bright stars hold their positions night after night, and constellations preserve their shapes. This steady appearance gives the impression of permanence. In reality, the calm outline is produced by distance and timescale. The stars are moving. The planets cross the background. Small bodies travel through the solar system. Some stars pulse, fade, or erupt. Some distant objects flare and then quiet again. Even the most stable-looking field is not truly still. The human eye cannot hold enough light long enough, or compare one night to another with enough precision to reveal the full pace of change. The southern sky is full of motion hidden inside apparent stillness. That hidden activity is one reason it matters to map the sky as a living scene instead of a single image. Its darkness is also deceptive. Black space between bright stars may seem empty, but visible darkness in astronomy often means only that light is weak, scattered, blocked, or spread too thinly to stand out. Much of the universe does not shine strongly in visible light. Much of what does shine is so far away that it appears only as a dim trace. The night sky teaches a simple fact. Seeing depends not only on what exists, but on what reaches the eye and how much of it can be collected. A richer view of the southern sky does not create new matter. It reveals matter and structure that are already there, waiting below ordinary thresholds of brightness, scale, and time. The southern sky also carries special value because it includes some of the clearest visible expressions of the nearby universe. The Large Magellanic Cloud and the Small Magellanic Cloud drift there as companion galaxies to the Milky Way, close enough to be studied in detail and large enough to show stellar populations across wide areas. Dense star fields arc through the band of the Milky Way, where gas, dust, and star clusters crowd the view. Far from that crowded band, darker windows open toward deeper space, and these clearer directions reveal great numbers of background galaxies. The same sky can therefore show structure within one galaxy and structure across the universe beyond many galaxies. This overlap gives the southern sky unusual scientific richness. When astronomers speak of surveying the sky, they mean more than looking. A survey is a planned, repeated, systematic record. It seeks coverage rather than a single chosen target. It values completeness, comparison, and measurement. In the case of the southern sky, a survey aims to transform scattered views into an organized account of what is present, how bright it is, where it lies, and whether it changes. This way of working turns the sky from scenery into data, yet the sky itself remains the same physical reality light arriving from many distances, shaped by stars, dust, galaxies, gravity, and time. There is also a quiet historical dimension in this field of view. Every part of the southern sky has been seen before by human eyes, but not every part has been measured with equal depth, regularity, or sensitivity. Large regions have remained underdescribed not because they lack importance, but because the tools needed for wide and repeated observation have been limited. A sky can be known in outline while remaining unknown in detail. It can be charted and still remain incomplete. It can be photographed and still remain only partially understood. The thought that a new observatory may reveal a sky never truly seen does not mean the sky has been absent. It means earlier views have not captured its full density of faint light, its full inventory of changing objects, or its full continuity through time. So the southern sky, taken on its own terms, is both familiar and unfinished. It is the same night field that arches above mountains, deserts, oceans, and cities across the lower half of the globe. At the same time, it is a region whose visible contents extend far beyond ordinary seeing. It contains nearby stars, distant galaxies, obscuring dust, sparse halos of light, crowded stellar rivers, apparent emptiness, and slow or sudden change. It is not a flat map, but a layered depth of reality. It is not silent in activity, only quiet to limited senses. To begin here is to begin with the widest region of the subject, where the eye meets the universe as a field. In that field, the first lesson is simple and steady. The sky is larger, denser, dimmer, and more active than it appears, and the southern sky holds that truth across an enormous span of darkness and light. Beyond the brighter pattern of nearer stars, the southern sky contains a far deeper layer that does not announce itself easily. It lies spread across the background as a countless population of galaxies, each one a city of stars, gas, dust, and dark matter held together by gravity. Most are too faint to stand out to unaided sight. Even through many ordinary telescopes, they appear only as small, pale shapes or soft points of light. Yet this distant background forms one of the largest visible components of the sky, where the eye sees darkness between bright stars. Sensitive observation reveals remote galaxies placed one behind another through depth. A galaxy is a vast system of stars and interstellar material bound into one larger whole. Some galaxies are spiral systems, with stars and gas arranged in broad turning arms around a brighter centre. Some are elliptical systems, rounder and smoother in appearance, with older stellar populations and less cool gas. Some are irregular, lacking a simple form because of past disturbance, active star formation, or small size. Rubin Observatory is built to record this distant population not one object at a time, but across immense sky areas. In that way, the background becomes what it truly is, a crowded universe of separate islands of matter and light. Distance changes how this background is seen. Nearby galaxies can show visible shape, color differences, dust lanes, or star-forming knots. More distant galaxies become smaller, dimmer, and less easily distinguished. Their light is weaker because it spreads over great distances before reaching Earth. Their appearance is also altered by time. Light does not arrive instantly. It travels at a finite speed through space, so distant observation is always delayed observation. A galaxy seen across millions of light years is seen as it was millions of years ago. A galaxy seen across billions of light years is seen in a far earlier stage of cosmic history. The distant background is therefore not only a backdrop in space, it is also a record through time. This makes a deep sky image unlike an ordinary landscape. In a landscape, distant hills and nearby trees exist at the same present moment for the observer. In the sky, the observer receives a mixture of moments. The nearer and the farther lights arrive together, but they do not all belong to the same age. The background of galaxies is a layered historical field. Each patch of sky gathers light released at different times under different conditions. Some galaxies in view are comparatively nearby. Others belong to a younger universe, when stars were forming under earlier cosmic conditions and galaxy structures were still developing. Careful measurement is needed to turn that blended light into a clearer account of cosmic structure. Color helps in that work. In astronomy, color is not merely decoration. It carries information about temperature, stars, dust, and distance. Blue regions in galaxies often indicate younger, hotter stars. Redder tones can reflect older stellar populations. The effects of dust, or the stretching of light during its long travel through an expanding universe. That stretching is called redshift, meaning that light from distant galaxies is shifted toward longer wavelengths as space expands. Rubin records the sky through several filters, each passing a different band of light, so the background population can be compared in a more organized way. Even a small patch of deep sky can contain extraordinary abundance. Rubin's early public imagery offers one strong example by showing part of the Virgo cluster region, where the view is crowded with galaxies scattered across a dark field. Some appear large enough to show shape. Many others are so small that they resemble grains of distant light. The deeper lesson is scale. A single field contains far more structure than human sight usually expects. Galaxies are not rare decorations placed occasionally across the universe. They are the ordinary large-scale units of visible cosmic matter. This abundance matters because galaxies are not randomly sprinkled without pattern. On the broadest scales, they trace a cosmic arrangement shaped by gravity over billions of years. Groups gather into clusters. Clusters connect along larger filaments. Wider gaps open between denser regions. The distant sky background therefore carries the visible imprint of how matter has collected across time. A survey that records great numbers of galaxies across wide areas can reveal not only individual systems, but the distribution of many systems at once. Faintness remains one of the great practical barriers. Distant galaxies often sit near the edge of detectability. Their light is not absent, but slight. To reveal them, An observatory must collect enough photons, meaning individual packets of light, and separate real sources from noise, glow, and instrumental limits. This is why depth matters. A deeper view reaches farther down into the sea of weak light. It brings previously unrecorded galaxies into the scientific picture and improves the measurement of those already detected. Rubin's role in this background is defined by breadth joined to depth. Many telescopes have looked deeper into tiny fields. Many have surveyed broad areas with less sensitivity. Rubin joins these aims on a remarkable scale, recording very large areas while still reaching faint sources and then returning again over many years. In the distant background, this means a growing inventory of galaxies measured across a huge span of sky under a common observing system. The value of such consistency is quiet but powerful. So the distant cosmic background is not an empty stage behind the brighter foreground of the night. It is one of the main realities of the visible universe. It contains innumerable galaxies, each carrying its own stars and history, each sending ancient light into the present. It transforms the blackness of the sky into a layered archive of structure through space and time. Under patient observation, the background becomes denser, more ordered, and more meaningful. What first appears as darkness resolves into a universe crowded with remote systems, and the southern sky begins to show that its deepest visible layer is already full. The night sky changes even when it appears calm. Its most familiar pattern gives little sign of this. Bright stars rise and set in expected ways. Constellations return with the seasons. The broad field seems stable enough to memorize, yet the visible sky is not a fixed arrangement pinned above Earth. It is a moving and changing mixture of objects, each following its own path or passing through its own cycle. Some changes are slow and only become obvious over years. Some unfold over months or days. Some happen in hours, minutes, or less. The changing night is therefore not a special part of the sky added on top of a steady one. Change is part of what the sky is. Movement is one kind of change. Planets wander against the star background because they orbit the sun at different distances and speeds. Asteroids shift position night by night, and sometimes hour by hour, as they travel through the solar system. Comets may enter the inner solar system, brighten, grow a visible coma, and then fade again. Even stars are moving through space, though most are so distant that their motion across the sky is subtle and slow to human notice. Nearby stars can drift by tiny amounts over time, gradually altering the map. The sky seems fixed mainly because distance smooths motion into stillness. Brightness is another kind of change, and it is far more widespread than older sky watchers could have measured in a complete way. Many stars do not shine at an absolutely steady level. Some expand and contract, causing regular pulses in brightness. These are variable stars, meaning stars whose light changes with time. Some stars dim because one member of a pair passes in front of the other from Earth's point of view. Some flare because of magnetic activity near their surfaces. Some brighten suddenly near the end of life, or because matter falls onto a dense companion. The important fact is not simply that unusual stars change. Large numbers of ordinary-looking stars also vary, gently or strongly, on timescales that differ from one case to another. On still larger scales, entire stellar deaths can briefly change the appearance of the sky. A supernova is an exploding star, or in some cases the violent destruction of a dense stellar remnant after it gains too much mass. For a short time, one distant point can brighten so strongly that it outshines a whole host galaxy around it. Then it fades, Such an event may take days to rise and weeks or months to decline. It leaves behind debris, altered matter, and sometimes a compact remnant such as a neutron star or black hole. Though rare for any one galaxy, supernovae are common across the immense number of galaxies visible in the sky. This means the changing night contains a steady supply of these short-lived events somewhere in the background. There are also outbursts around black holes. In some galaxies, a central black hole gathers matter from surrounding gas or from a disrupted star. As matter falls inward and heats, the galaxy's central region can brighten. In rarer moments, a star passes too close to a massive black hole and is torn apart by tidal forces, meaning different gravitational pulls across its body. Part of its material falls inward and produces a flare that slowly changes over time. Elsewhere, matter moves between close stars in binary systems and causes repeated brightenings. The night is therefore alive not only with motion and pulses, but with temporary releases of energy from matter under extreme conditions. Some changes are not truly sudden in nature, only sudden in detection. A faint object may remain below visibility until conditions improve or enough light is gathered. A small moving body may be present in an image, but only become clear when its position is compared across several observations. A distant flare may begin before anyone notices it. The changing sky is partly a matter of the universe acting, and partly a matter of whether observation is repeated often enough to catch the act. This makes time itself part of seeing. A single image shows where light is at one moment. A sequence shows that the sky is a process. This process extends from the nearest scales to the farthest. Near Earth, artificial satellites cross the field in straight tracks, though they do not belong to the natural sky. Within the solar system, asteroids and comets shift against the stars. Within the Milky Way, stars pulse, eclipse, flare, and drift. Beyond the Milky Way, active galactic nuclei brighten and fade. Supernovae rise and fall, and rare gravitational alignments can briefly change the apparent brightness of distant sources. The changing night is therefore layered, just as the deep sky is layered. Near and far objects both participate, but on different scales and for different physical reasons. To describe the night as changing is also to speak of incompleteness in older viewing. Traditional astronomy has always known about motion and periodic behavior, but the full variety of change across the sky has been difficult to capture at once. Many earlier observations focused on selected objects, limited fields, or special events already noticed by chance. What remains harder is a broad and regular accounting of change across an enormous sky area over long periods, without such repetition. Many kinds of variation remain hidden, not because they are rare, but because they are easily missed. The changing night therefore teaches a simple scientific lesson. The universe is not only made of things, it is made of events, cycles, encounters, and transitions. A star does not merely exist. It forms, burns, pulses, loses mass, interacts, and dies. A small body does not merely occupy a place. It moves through the solar system and changes position from one night to the next. A distant galaxy is not merely a faint patch. It may host explosive deaths, feeding black holes, and other temporary flashes. Time turns the sky from a map into an unfolding record. From a human point of view, this can remain almost invisible. The night seems quiet because its changes are spread across immense distances and mixed time scales. Yet the quiet is only apparent. The field overhead is active in every direction. Countless objects are shifting, brightening, dimming, erupting, or passing by. The sky remains serene in appearance, but underneath that serenity lies continuous change, waiting for patient observation to bring it into view. Closer than the deep background of remote galaxies lies a brighter and more crowded foreground. This is the visible body of the Milky Way, the galaxy that contains the Sun and all the familiar stars of the night. When seen across the southern sky, it does not appear as a separate object with a clear outer edge. It appears as a band, a haze, a thickening of starlight, and in some regions a river of brightness cut by darker seams. That appearance comes from position. Earth lies within the Milky Way's flat stellar system, so when the eye looks along the dense plane of the galaxy, the number of stars rises sharply. Instead of viewing the galaxy from outside, the observer looks through it from within. This foreground is rich because it is local by cosmic standards. Its stars are not all nearby in an everyday sense, since many lie thousands of light years away, but they are still far closer than the galaxies beyond the Milky Way. Their relative nearness makes them brighter, larger in apparent spread, and more numerous across the field. The distant universe often appears as scattered points and dim shapes separated by darkness. The Milky Way foreground, by contrast, can become dense enough that darkness itself seems reduced, not because space is full everywhere, but because so many stars gather along the line of sight. Yet even this bright foreground is not simple. It is made of overlapping populations. Some stars are young and hot, shining with a bluish light, and often found near clouds of gas where recent star formation has taken place. Some are older and redder, belonging to longer and quieter stages of stellar life. Some are arranged in clusters, groups of stars born from the same cloud and still moving together. Others are spread more broadly through the galactic disk, the flattened main body of the Milky Way. Beyond the disk, a thinner halo of stars surrounds the galaxy in a much sparser arrangement. The foreground therefore has its own internal depth, with stars at different distances, ages, and paths all mixed into one apparent scene. Dust shapes much of what is seen here. Interstellar dust consists of extremely small solid grains mixed into the gas between stars. Though thinly spread, dust has a powerful visual effect because it blocks and scatters light. In regions where dust gathers more densely, bright star fields behind it are dimmed or hidden, and the Milky Way's glowing band is cut by dark lanes and patches. These dark areas are not holes in the galaxy. They are curtains laid across brighter layers behind them. In visible light, dust can make a crowded field look broken and uneven. It can also redden the stars that remain visible, because shorter wavelengths are scattered more strongly than longer ones. Rubin's early imagery of the Trifid and Lagoon nebulae gives a clear example of this Milky Way foreground in action. There, glowing gas, embedded star fields, dark dust lanes, and nearby stellar groupings share one region of sky. The field is not orderly in a geometric sense. It is textured, layered, and active in appearance. Dust threads across bright emission clouds. Clusters of stars appear inside or near the nebulous structure. Fainter stars fill the gaps between brighter ones. Such a scene shows why the foreground of the Milky Way cannot be reduced to a simple background of points. It is a living structure of gas, dust, and stars under the influence of gravity and stellar radiation. In practical observation, the Milky Way foreground can both reveal and conceal. It reveals the local structure of the galaxy because the richness of stars allows astronomers to study stellar populations, distances, motions, and the broad shape of the galactic disk and halo. At the same time, It conceals more distant objects because dense star fields and dust make it harder to isolate faint background galaxies. A single region may therefore be valuable for one kind of science and difficult for another. This is not a flaw in the sky. It is a consequence of looking outward from inside a galaxy rather than from a detached and clearer external position. The stars of this foreground are not identical lamps. They vary widely in mass, temperature, colour, size, and lifetime. A massive star burns its fuel quickly and lives for a relatively short time. A smaller star can shine much longer and more steadily. Some stars remain on the main sequence, meaning the long stage in which hydrogen fuses into helium in the core. Others have expanded into giant phases. Some are compact remnants of earlier stellar lives. These differences shape the Milky Way's visible texture. Blue stars often mark younger regions. Red giants add warmer tones to older populations. Dense clusters collect stars into recognizable knots. The broad galactic band becomes a record of many generations of star formation layered together. Variation is also common in this nearer field. Many of the stars seen in the Milky Way foreground change in brightness over time. Some pulse because their outer layers expand and contract in a regular way. Some are eclipsing pairs, where one star passes in front of the other and causes repeated dips in light. Some flare because of magnetic activity. These changes may be small or large, slow or quick, regular or irregular. In a crowded stellar field, such behavior is not exceptional. It is part of the ordinary life of stars. The foreground, therefore, contains not only many stars, but many changing stars. The importance of this region lies partly in its familiarity. Human beings have always looked first at the stars of the home galaxy. The Milky Way is the most immediate large-scale structure of the universe visible to ordinary sight, but familiarity can hide complexity. A bright band across the sky may seem well known simply because it is often seen. In fact, its full richness only emerges when the field is measured deeply, repeatedly, and across wide areas. Then the foreground begins to resolve into distinct stellar streams, clustered populations, variable stars, obscuring dust, and fine structure spread through the galaxy's body. So this foreground is the first truly local great layer of the southern sky. It stands between Earth and the distant background, bright enough to dominate many fields, structured enough to tell the story of a life inside a galaxy, and complex enough to resist any simple description. It is the Milky Way seen from within, dense, dusty, star-filled, and uneven, carrying nearby history across the sky as a visible presence. Across the wider stillness of the sky, some bodies do not remain fixed in place even for a single night. They cross the field. They shift against the background of stars and galaxies because they belong to the solar system, a local family of objects orbiting the sun at many distances and on many paths. In the deepest background, a galaxy may hold its place and appearance across human lifetimes. In the nearer foreground of the Milky Way, stars seem almost fixed from one night to the next, but solar system bodies move in a different way. Their nearness makes motion visible. Their orbits carry them from one part of the sky to another. Their changing positions turn the sky into a place of local passage as well as distant light. An asteroid is a small rocky or metallic body left over from the formation of the solar system. Most asteroids travel in the broad belt between Mars and Jupiter, though many follow other paths. Some move closer to Earth. Some share the orbit of larger planets in stable gravitational regions. Some occupy the far outer solar system beyond Neptune. What joins them is not size alone, but the fact that they are minor bodies orbiting the Sun and changing their place against the background stars. They do not glow by their own light. They are seen because sunlight falls on them, and a small part of that light is reflected outward into space. This reflected light is often faint. Small bodies are difficult to see not because they are unimportant, but because they are small, dark, distant, or fast-moving, and often all of these at once. A large telescope can reveal them, yet seeing them once is not enough. A point of light becomes a moving object only when its position is compared over time. This makes repeated observation essential. A single image may contain an asteroid without identifying it as such. A sequence of images allows the object to separate itself from the fixed background by motion. Time again becomes part of seeing. The main asteroid belt supplies a great many of these crossings. Bodies there orbit between Mars and Jupiter and move in related directions around the Sun, though with a wide range of orbital periods, inclinations, and sizes. In images taken over time, they can appear as shifting points threaded through the same star field. Their motion is not random, it follows the geometry of orbits, the relative position of Earth, and the pace at which each body moves around the Sun. Yet from the point of view of the night sky, the effect is lively. A field that seems still when treated as a map becomes active when small local worlds begin to drift through it. Near-Earth objects form another important group. These are asteroids or comets, whose orbits bring them relatively close to Earth's own orbital path. They matter because they help preserve a record of solar system history, and because some may one day pose impact risk if their paths intersect Earth at the wrong time. Most are not dangerous. Many are simply part of the ordinary traffic of the inner solar system. Still, their discovery and tracking carry practical importance. A moving object cannot be understood by brightness alone. Its path must be measured, and from repeated measurements its orbit can be calculated. Only then does a wandering light become a known body with a place in the solar system's larger arrangement. Farther out, another population shares space with Jupiter. These are the Jupiter Trojans, small bodies gathered around stable regions along the giant planet's orbit. They travel with Jupiter, one group leading the planet and another trailing behind. Their existence shows that the solar system is not organized only by simple circles around the Sun. Gravity creates special regions where bodies can remain collected for long periods. These objects are more distant and often fainter than many near-Earth bodies, but they too can cross a survey field and reveal their presence by steady motion over time. Beyond Neptune lies an even colder and more remote population. These outer bodies include trans-Neptunian objects, icy remnants from the solar system's early formation that orbit far from the Sun. Because they are so distant, their movement across the sky appears slower. Their reflected light is also weaker, and many remain difficult to detect. Yet they are valuable because they preserve ancient material from the solar system's outer regions. In them, the early conditions of planetary formation remain written in a quieter, less altered form. When such an object crosses a field, it does so with patience rather than speed. But its passage still marks the same truth: the sky contains local bodies moving through a larger fixed background. Comets belong to this crossing world as well. A comet is an icy body that can develop a visible coma and sometimes a tail when sunlight warms its surface and releases gas and dust. Far from the Sun, a comet may appear faint and compact. Closer in, it can grow diffuse and extended, making its motion visible in a more dramatic way than an asteroid's simple point of light. Even so, the basic principle remains the same. It is an object of the solar system following an orbit, reflecting sunlight and changing appearance as its distance from the sun changes. The movement of all these bodies reveals something profound about the sky. Not every light overhead belongs to the deep universe. Some belong to the immediate cosmic neighborhood of Earth. They are not fixed stars at vast remove, but nearby matter in motion around the same sun that lights Earth by day. This gives the night a local dimension. The sky is not only a window outward to galaxies and remote cosmic time, it is also a screen across which the leftover building blocks of planets, the icy bodies of the outer system, and the small wanderers of near space make themselves briefly visible. Rubin Observatory's early public results show how rich this local traffic can be when the sky is observed with enough sensitivity and repetition. In only a short span of observations, many previously unseen moving bodies become visible, crossing fields that also contain stars and galaxies fixed in apparent place. This contrast is important. The moving objects stand out not because the sky around them is empty, but because the deeper universe behind them is so steady on human timescales. Motion belongs to nearness. Stillness belongs, in appearance, to remoteness. So this region of the subject remains within the sky itself, but it brings the view inward to the solar system's travelling bodies. They pass through the field as brief crossings against a much older and more distant backdrop. Their light is borrowed from the sun. Their paths are shaped by gravity. Their presence reminds the observer that the night sky contains not only far-off history, but nearby movement unfolding in real time. Before light from the southern sky reaches any mirror, lens, or sensor, it passes through air. This air is transparent enough to make astronomy possible from the ground, yet never perfectly transparent. It forms a changing layer between Earth and space, a moving medium of gas through which every ground-based observation must look. The night sky may seem to rest directly above the land, but from the point of view of observation, it is filtered first through the atmosphere. This makes the atmosphere the first physical region of Rubin Observatory's subject, the nearest boundary through which distant light must travel before it can become part of a measured image. Earth's atmosphere is made mainly of nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, water vapor, and other trace gases. These gases are thin compared with water or rock, but over the full depth of the atmosphere they're enough to bend, scatter, absorb, and blur incoming light. None of these effects means the atmosphere is hostile to all observation. Without a transparent atmosphere, the stars would not be visible from the ground at all. The important point is steadier and more exact. Air allows sight, but imperfectly. Astronomy from Earth always begins by understanding that light arrives altered by the path it takes through the moving gas above the surface. One effect is simple dimming. As light passes through air, a small part of it is scattered away or absorbed. This means an object closer to the horizon often looks dimmer than the same object high overhead, because its light crosses a greater thickness of atmosphere. Another effect is color change. Shorter wavelengths are scattered more strongly than longer ones, which is one reason the daytime sky appears blue and sunsets can appear redder. At night, the same physical processes remain present, though the effect is subtler in astronomical work and must be measured carefully. Water vapor matters especially because it can absorb some wavelengths and also affects how stable and clear the air is. Dry air is usually better for observation than moist air, not because moisture blocks all starlight, but because water in the atmosphere increases absorption, turbulence, and cloud formation. Thin clouds, haze, or moisture that may seem minor to ordinary sight can still reduce the quality of precise astronomical images. A night that looks clear to the eye may not be equally clear to a telescope designed for exact measurement. Turbulence is one of the most important atmospheric effects. Air is not motionless. It rises, sinks, mixes, and flows in layers with different temperatures and densities. These changes alter the refractive index, meaning the degree to which light bends as it moves through the air. When light from a star crosses many small pockets of air with slightly different properties, its path is disturbed again and again. To the eye, this can make stars twinkle. To a telescope, it causes images to blur and shimmer, limiting sharpness. The atmosphere does not erase the sky, but it prevents ground-based observation from reaching the stillness of space. This blurring is often described in astronomy as seeing, a practical term for the steadiness or unsteadiness of the atmosphere from an observing sight. Good seeing means the atmosphere is stable enough that stars appear less spread out, and fine detail is preserved more clearly. Poor seeing means turbulent air broadens images and washes out small structure. Good seeing does not depend on one factor alone. It reflects temperature gradients, wind patterns, local terrain, and the broader movement of air above the region. The atmosphere, therefore, has its own weather for astronomy, distinct from ordinary ideas of rain or comfort. Darkness is also part of atmospheric quality. Even when the sky is cloudless, light from cities, roads, or settlements can scatter in the air and brighten the background. This is light pollution, and it reduces contrast between faint cosmic sources and the sky itself. Air that is physically clean and dry can still carry scattered artificial light if bright human development lies nearby. For a survey observatory that aims to record very faint objects across wide fields, preserving dark sky is essential. Darkness is not the absence of atmosphere, but the absence of excess scattered light within it. The atmosphere also glows faintly on its own. High in the upper layers, chemical processes can produce a natural emission called air glow. This glow is weak, far weaker than daylight, but sensitive instruments detect it as part of the sky background. It changes slowly across time and contributes to the fact that the night is never completely black from the ground. Rubin Observatory must therefore look not through a silent medium, but through one that adds a small and shifting brightness of its own. Yet for all these limitations, the atmosphere remains an extraordinary partner in ground-based astronomy. It is transparent across the visible range that Rubin uses. It allows immense telescopes to operate from Earth instead of requiring every major survey to be placed in orbit. It makes repeated, wide-field observation practical on scales that would be far more difficult and costly in space. The task is not to remove the atmosphere, but to work with its best conditions, measure its effects, and choose a place where those effects remain as gentle as possible. This is why the air above an observatory is not an empty gap between instrument and stars. It is an active optical region. Light from galaxies, stars, nebulae, and solar system bodies descends through it and is slightly reshaped along the way. Some light is lost, some is bent, some is blurred. Some background brightness is added. The atmosphere acts on every source equally in the sense that none can avoid it, yet differently in the sense that horizon, colour, season, and moment all affect the exact result. So the first inward step from the sky itself is this moving shell of gas around Earth. It is calm enough to let the universe be seen, but restless enough to make precision difficult. It softens the sharpness of distant points, dims faint sources, scatters unwanted light, and sets the first conditions under which any ground-based image must be made. For Rubin Observatory, every observation begins here, in air that is clear, dark, dry, and never perfectly still. Below the moving air and above the lower valleys, the mountain summit becomes the next necessary region in the inward path. The sky may be the subject of observation, and the atmosphere may be the medium through which light travels. But a ground-based survey still needs a place to stand. That place cannot be chosen casually. It must offer darkness, dryness, height, stability, and a broad view of the sky. For Rubin Observatory, that place is Cerro Pachon in northern Chile, a high mountain site in the Andes where the land itself supports the kind of long, repeated observing that the survey requires. A mountain summit matters first because height removes part of the atmosphere from the line of sight. At greater elevation, there is simply less air above the telescope than there would be at sea level. This does not eliminate atmospheric effects, but it reduces some of them. The light from stars and galaxies still passes through air, though through a thinner column of it. In practice, that means better transparency, lower absorption in some conditions, and often steadier viewing than would be possible lower down. Height is therefore not a symbolic advantage. It is a direct physical benefit for seeing the sky more clearly. Cerro Pachon stands more than 2,600 meters above sea level. At that altitude, the summit lies in a dry mountain environment where the air is often clear and the number of usable nights is high. The site belongs to a broader region already known for astronomical observing. Other major observatories operate nearby on related mountain terrain, not because the peaks are dramatic to the eye alone, but because the climate and geography repeatedly prove their value to astronomy. The mountain is part of an observing landscape, a place where land, air, and darkness come together in a favourable way. Dryness is one of its great strengths. Northern Chile contains some of the driest conditions on Earth, and that matters deeply for astronomy. Moisture in the air can interfere with observation through absorption, haze, and cloud formation. A dry summit does not guarantee perfect skies every night, but it increases the chance that the air remains transparent and stable. Dry ground and dry air also reduce many of the small local effects that can trouble precision observing. A mountain that sheds heat after sunset in a predictable way, and that does not sit beneath frequent cloud cover, provides a calmer visual path upward into the night. Darkness also shapes the value of the site. Cerro Pachon is far from the brightness of large urban centres, and that distance protects the sky from much scattered artificial light. Faint galaxies, dim variable stars, and subtle sky structure become harder to detect when the night background is brightened by human illumination. For a survey that aims to return to the same fields repeatedly and measure small changes, preserving dark conditions is not an added luxury. It is part of the scientific foundation of the work. A dark summit allows weak light from distant objects to stand out more cleanly against the sky. The mountain's geography supports another important quality, which is openness of view. Rubin Observatory is designed to observe a great expanse of the southern sky over and over. That requires not only good weather, but a site where the horizon and the accessible sky are not heavily blocked by surrounding terrain. A summit on a ridge gives a wide visual reach. It places the observatory high above many local obstacles and allows the sky to be followed across broad arcs. This is especially important for a survey that does not dwell only on one narrow target, but moves across large sky areas as part of a repeated program. Yet a good mountain site is not simply remote and high, it must also be physically sound. Cerro Pachon lies in a tectonically active region, where earthquakes can occur, as they do across much of Chile. This means that stability must be understood in a deeper engineering sense. The summit rock and the way structures are anchored into it matter greatly. A survey telescope cannot rest on loose ground or on a foundation that transmits every vibration into the instrument. The mountain must provide not only height and darkness, but firm bedrock capable of supporting a large and precise observatory over many years. The summit environment also has its own harshness. High altitude brings stronger exposure to wind, cold, nighttime temperatures, and demanding conditions for construction and maintenance. The dryness that benefits astronomy can also make the landscape severe. Dust, temperature swings, and isolation all become part of life on the mountain. This means the site is scientifically excellent precisely because it is not especially gentle for ordinary human activity. The same qualities that make the summit suitable for observing make it a place where every building, road, cable, and support system must be carefully planned. Even the living landscape reflects this character. Cerro Pachón is not barren in an absolute sense, but life there is adapted to thin, dry, high ground, shrubs, cacti, birds, small mammals, and hardy mountain species belong to the region. Their presence reminds the observer that the site is not an abstract platform built outside nature. It is part of a real mountain ecosystem shaped by altitude, dryness, and exposure. Astronomy at such a place depends on coexistence with that environment rather than separation from it. There is a quiet discipline in choosing such a summit for a decade-long survey. The mountain does not observe the sky. It only makes observation possible by offering the right conditions with unusual consistency. It is the stable ground beneath repeated looking. In that sense, Cerro Pachón becomes part of the instrument, not because it contains machinery, but because its physical qualities are inseparable from the quality of the observations made there. A less suitable mountain would produce a different survey. A brighter, lower, wetter, less stable site would change what the observatory could see and how well it could see it. So the inward path now reaches the land itself, where the sky-facing work of Rubin Observatory is given a home. Cerro Pachón is not chosen for scenery or isolation alone. It is chosen because elevation, dryness, darkness, openness, and solid ground combine there in a rare and practical way. The summit turns a mountain into a scientific platform. It holds the observatory between earth and sky, high enough to reduce some of the atmosphere, far enough from cities to preserve darkness, and firm enough to support the long patience of a repeated survey. At the summit, the observatory does not stand exposed to the mountain air as an uncovered machine. It lives inside a shell. This outer structure is not a decorative housing placed around the real instrument. It is the first built boundary of the observing system, the part that stands between the harsh conditions of the summit and the precision required for night after night of survey work. Rubin Observatory's enclosure marks the point where open mountain, moving air, and falling temperature meet controlled architecture. It is the observatory's weather-facing skin. From a distance, the enclosure appears as a large rounded form set beside a long lower building. The shape reflects purpose rather than monument. A survey telescope must move quickly, open widely to the sky, remain stable in wind, and close securely when weather turns against observation. The enclosure answers these needs by combining protection and motion in one structure. It is not a fixed shell with a simple opening. It rotates. It aligns itself with the telescope's changing direction. It opens the path to the sky only where needed, and closes again when protection is required. This rotating outer form is often called the dome, though Rubin's enclosure is more specialized than the older image that word can suggest. In many traditional observatories, a dome primarily protects a telescope that points through a narrow slit while following selected targets. Rubin's work is broader and faster. It is built for a wide-field survey that moves repeatedly across large areas of sky. That kind of observing asks more from the enclosure. The structure must not only allow access to the sky, it must allow efficient, repeated repositioning while limiting the effects of wind, dust, and thermal disturbance. Wind is one of the summit's constant concerns. Even on clear nights, moving air can shake structures, introduce vibration, and disturb the air inside an observatory if the outer shell is poorly designed. The enclosure therefore serves as a wind buffer as much as a weather barrier. When open, it does not remove the atmosphere from the observing path, but it can reduce the direct mechanical effect of gusts on the telescope and help control how air flows around the instrument. This is a subtle but important role. Good observing depends not only on clear skies overhead, but also on keeping the local environment around the telescope from becoming a source of blur and vibration. Temperature matters just as much. During the day, buildings absorb heat from the sun. At night, that stored heat can leak into the air around the telescope and create local turbulence. Warm air rising from floors, walls, or machinery can disturb incoming light just as surely as unstable air higher in the atmosphere. For this reason, the enclosure must be more than strong. It must also be thermally disciplined. Surfaces, ventilation, and internal arrangements are planned so that the structure does not become a quiet source of image degradation. In astronomy, a building can harm seeing even when the sky itself is good. Rubin's shell exists in part to prevent that. The long attached support building gives the summit structure a distinctive form. This lower extension is not where the sky is observed directly, yet it is essential to the shell's function. It houses many of the systems that allow the observatory to operate, maintain stable conditions, and support the instrument. Mechanical equipment, electrical systems, cooling and service functions, access levels, and maintenance areas all belong to this broader built body. The enclosure is therefore not only a rotating upper form, it is part of a larger summit facility in which protection, control, movement, and support are joined into one working whole. There is also a rhythm to how such a shell lives through time. By day, the enclosure remains closed, protecting the observatory from sunlight, dust, changing mountain weather, and unnecessary thermal loading. By night, when conditions permit, it opens to the sky and becomes something different. It does not disappear, but its role shifts from shield to guide. The opening frames the region of sky being observed. The enclosure turns with the telescope. Its moving parts must remain reliable over many years because the survey depends on repetition. A structure that opens only beautifully on special occasions would not be enough. Rubin's shell must perform steadily, night after night, through the long patience of the project. Protection from earthquakes also shapes this region. Cerro Pachon lies in Chile, where seismic activity is a real part of the environment. The enclosure and surrounding summit structures must therefore be engineered with strong attention to stability and isolation. This does not mean the shell prevents earthquakes in any simple sense. It means the built system is designed so that large structural motions do not easily pass into the precision components that must remain aligned. The observatory shell thus belongs to a mountain landscape where ordinary architectural concerns are joined by the deeper demand of scientific accuracy under difficult natural conditions. Its scale is important because the instrument inside is itself large, yet the shell cannot simply become massive and still be considered suitable. An enclosure that is too heavy in motion, too slow to turn, or too crude in airflow would work against the telescope it is meant to protect. Rubin's shell must therefore balance size with responsiveness. It has to be strong enough for the summit, open enough for efficient observing, and controlled enough not to become its own source of problems. This is a quiet kind of engineering, where success often appears as absence. The best enclosure draws little attention to itself because it does not interfere. Seen in this way, the observatory shell is neither scenery nor mere container. It is the outer built organ of the survey, the layer where architecture begins to participate directly in astronomy. It translates mountain conditions into workable observing conditions. It keeps out weather, limits dust, moderates wind, manages heat, supports motion, and shelters the instrument when the sky cannot be used. It is the observatory's first machine-sized answer to the exposed summit, so the inward path now reaches the enclosure itself, the large moving shell on Cerro Pachon that turns a harsh mountaintop into a controlled astronomical workplace. Outside it are darkness, wind, cold, dust, and the full openness of the mountain. Inside it, conditions are shaped for precision. The shell does not observe the universe, but without it the observing instrument could not endure the summit or work with the steadiness that the survey demands. Inside the enclosure, the next region is the telescope itself, the main observing body that gives Rubin Observatory its physical way of looking. This instrument is called the Simony Survey Telescope. It is not built to linger on one small target for long stretches in the manner of many traditional observatories. It is built to survey, meaning to cover large areas of sky in a systematic and repeated way. That purpose shapes its entire form. The telescope is not only large, it is fast in operation, wide in reach, and designed to move with steadiness from one field of sky to another through the course of a night. A telescope, in the most basic sense, is a machine that collects light from distant objects and directs it into a form that can be measured. The Simony Survey Telescope does this on a scale suited to a very wide field of view, meaning a broad patch of sky can be recorded at once, rather than a narrow pointed area alone. This matters because the southern sky is too large and too active to be studied fully by an instrument that sees only a tiny window at each moment and moves slowly between positions. Rubin's telescope body is therefore shaped by an unusual marriage of size and range. It gathers a great deal of light, but it also spreads its attention broadly. The telescope stands as a large mounted structure, able to turn in direction and altitude. One motion carries it left or right around the horizon. The other lifts it higher or lowers it toward the horizon. These two motions allow it to point across the accessible sky. Such movement sounds simple in principle, but in practice it must be extraordinarily precise. A telescope of this size has mass, and mass resists change. Yet the survey asks it to move often and settle quickly. The body must therefore be strong enough to carry heavy optical and camera systems, but balanced enough to reposition without wasting time or shaking itself into poor performance. Balance is one of the hidden virtues of such a telescope. An unbalanced instrument would strain its motors, respond unevenly, and transfer unwanted flexing or vibration into the line of sight. The Simony Survey Telescope is built so that its mass is distributed with careful attention to motion. It must lift, turn, and stop under control, then hold its pointing while an exposure is taken. After that it must move again. The survey depends on this repeated cycle. Precision here is not a matter of a single perfect pose. It is a matter of repeating accurate motion over and over through night after night and year after year. Speed is central to its identity. In astronomy, a fast telescope can mean more than one thing. It can refer to an optical system that brings light to focus over a short physical distance relative to its size, and it can also suggest a working instrument able to move efficiently through an observing plan. In Rubin's case, both meanings matter, though the telescope body is most easily understood by its behavior. It is a survey machine. It does not spend the night fixed on one small object, while the rest of the sky waits unseen. It travels from field to field, building an immense record through repeated brief visits. This gives the telescope a distinctive scientific character. Many large observatories are designed for selectivity. They point toward one chosen galaxy, one nebula, one exoplanet host star, one cluster, one spectrum. Their power lies in careful concentration. The Simone Survey Telescope serves a different style of astronomy. Its power lies in regular breadth. It turns the sky into a territory to be patrolled and recorded. The telescope body therefore acts less like a single investigating eye fixed on one place, and more like a disciplined observer sweeping across a huge domain according to plan. The instrument's size remains essential. Wide coverage alone would not be enough if faint objects could not be reached. A survey telescope must not only see broadly, it must gather enough light within each visit to detect subtle sources and record useful detail. Rubin's telescope body supports a primary mirror more than 8 meters across, placing it among the major large telescopes of the world. That scale allows the instrument to collect a substantial amount of light quickly, which is part of what makes a repeated wide survey practical rather than shallow. The telescope is therefore large not for prestige, but because the scientific task demands both reach and sensitivity together. Its mechanical structure also has to preserve alignment. A telescope of this kind carries major optical elements and a very large camera. As it points to different parts of the sky, gravity acts on the structure from changing directions. If the body flexes too much, the image quality suffers. For that reason, the telescope's frame and mount are engineered to remain rigid within very tight limits while still allowing motion. This is an important kind of strength. It is not stiffness for its own sake, but controlled stiffness that protects the geometry of the instrument while it works. The telescope also lives in close relationship with the summit conditions around it. Wind, temperature changes, and the moving enclosure all affect how comfortably and accurately it can operate. The body must therefore function as a stable system in a changing environment. It must keep its pointing under control, track the apparent motion of the sky during each exposure, and then step efficiently to the next field. Its work is neither passive nor dramatic. It is repetitive, measured, and exact. The greatness of such a telescope lies in disciplined endurance. There is also a quiet difference between seeing and recording. A traditional image of astronomy often imagines the telescope as an eye extended toward the heavens. That image contains some truth. But Rubin's telescope body is better understood as a survey platform for a larger observing chain. It collects and directs light, yes, but it does so in coordination with a very large digital camera and a long-term observing program. The telescope is thus not a solitary machine. It is the central moving body in a wider system devoted to repeated measurement. In this region of the inward path, the instrument appears as a whole before its internal light path is followed in detail. The Simone Survey Telescope stands inside the enclosure as the survey's working body. large enough to gather faint light, wide enough to see broad fields, and agile enough to revisit the sky again and again. It carries the observatory's central intention in mechanical form. It is the physical answer to a simple scientific need to look at an enormous sky not once, but systematically, with breadth, speed, and precision. Inside the telescope body, light does not travel straight from the open sky into the recording system. It is gathered, redirected, and shaped by a carefully planned optical path. This path is the next inward region of the observatory, the route by which faint light from distant stars, galaxies, nebulae, and moving solar system bodies is turned from a broad incoming stream into a controlled beam. Rubin Observatory uses a 3-mirror optical design for this task. The reason is practical and scientific at once. A survey telescope must not only collect much light, it must also preserve image quality across a very wide field of view. That is a demanding combination, and the mirror path exists to make it possible. A mirror in astronomy is not like a household mirror used for human reflection. It is a shaped optical surface built to reflect and focus light with high precision. The shape matters because a simple curved mirror does not keep all incoming rays equally sharp across a wide field. Light entering near the center of view and light entering from farther off axis can come to focus differently if the design is too simple. This leads to distortion and blur. Rubin's optical system solves this by using 3 aspheric mirrors, meaning mirrors whose surfaces are not simple spheres. Their more complex shapes help control optical errors and keep the image sharp across a broad area of sky. The first of these mirrors is the primary mirror, often called M1. It is the main light-gathering surface. When a broad patch of southern sky enters the telescope, this mirror intercepts the incoming light and begins to bring it inward. The size of the primary mirror is one of the reasons Rubin can detect faint sources efficiently. A larger mirror gathers more light, and more collected light means dim objects become easier to measure in a practical exposure time. But size alone would not be enough. The light must be directed in a way that supports both sharpness and breadth. After reflecting from the primary mirror, the light travels toward the secondary mirror, called M2. This mirror is convex, meaning it curves outward rather than inward. That shape may seem unusual, but it plays a vital role in the design. The secondary mirror redirects the converging light in a way that helps compress the optical path and correct the geometry of the image. It allows the telescope to remain more compact than a simpler design of equal reach might require. Compactness matters because a shorter and more balanced telescope can move more quickly and settle more efficiently between pointings. The mirror path therefore affects not only image quality, but the working rhythm of the whole survey. From the secondary, light continues toward the tertiary mirror, called M3. This third mirror redirects the light once more, sending it toward the focal region where the image will be formed. The presence of the tertiary mirror is one of the defining features of Rubin's design. It helps maintain sharp images over the telescope's unusually wide field. In a narrower telescope, such complexity might not be necessary. For Rubin, it is central. The observatory is not designed merely to look deeply at one tiny part of the sky. It is built to combine depth with breadth, and the third mirror is part of what makes that possible. An especially distinctive feature of Rubin is that the primary and tertiary mirrors are not separate glass pieces mounted apart from one another. They are formed together from one large monolithic structure, meaning one continuous piece of glass shaped into 2 optical surfaces with different curvatures. This combined mirror is often called M1M3. That design reduces the overall length of the telescope and improves structural stiffness. It also helps the optical and mechanical systems work together as one balanced whole. The mirror path is therefore not only a sequence of reflections, it is also a physical architecture in which optical design and mechanical design support each other. The order of the light path is steady. Light from the sky enters the telescope and reflects first from M1, then from M2, then from M3. At each stage, the beam is redirected and refined. The aim is not simply to make the light meet at one point. The aim is to form a wide, well-corrected image across a large focal surface. This is difficult because rays entering from different parts of the sky arrive at slightly different angles. A poor design would make stars near the edge of the field appear stretched or blurred. Rubin's mirror path is designed so that stars remain sharp from the center, outward across a much wider area than older, large telescopes usually provide. This broad, corrected field is one of the observatory's most important strengths. A telescope can be powerful in one of two general ways. It can be narrow and deep, or broad and efficient. Rubin aims for unusual power in the second sense while still preserving strong sensitivity to faint light. The mirror path makes that balance possible. It collects enough light to record dim sources while keeping the image usable across a very large field. In effect, the mirrors prepare a wide piece of sky to be captured all at once without sacrificing too much sharpness at the edges. Precision in the mirror surfaces is essential. These optical elements are polished to extraordinary accuracy because even tiny errors in shape can degrade the final image. Their alignment also matters. If the mirrors are not held in the correct relative positions, the wide-field image loses quality. The telescope therefore includes active systems that maintain the optical geometry as the instrument points to different parts of the sky and changes orientation under gravity. The mirror path is not a passive arrangement fixed forever after construction. It is a controlled optical relationship maintained continuously so the survey can remain consistent. There is a quiet elegance in this route of light. Light that has travelled for millions or billions of years reaches Earth, crosses the atmosphere, enters the telescope, and then meets three shaped mirrors in succession. Each reflection is purposeful, none is decorative. Together they turn a vast entering field into a corrected and concentrated image. The design does not seek simplicity in appearance, it seeks clarity in result. Its success lies in allowing a large telescope to behave as a wide-field survey instrument, rather than only a narrow pointing instrument. So the mirror path is the inner optical corridor of Rubin Observatory's telescope. It begins at the primary mirror, passes to the secondary, continues to the tertiary, and emerges as a carefully shaped beam ready for the next stage of measurement. Here, the broad sky is transformed into ordered light. The mirror system gathers, redirects, and corrects it, preserving both faintness and field. In this region, the observatory's central promise becomes physically real. A wide sky can be brought into focus with remarkable sharpness and speed. After the light has been gathered and corrected by the mirror system, it reaches the entrance of the camera. This is the next inward region of Rubin Observatory, where the broad image formed by the telescope passes into a more enclosed and controlled optical space. The outer sky has already been narrowed into a precise beam. Now that beam must enter the camera without losing the image quality so carefully prepared by the mirrors. The camera entrance and the filter system together shape this passage. They do not create the sky image from nothing. They preserve it, refine it, and organize it before the light reaches the recording surface deeper inside. The Rubin camera is immense by astronomical standards, and its front opening is part of what makes that scale necessary. A very wide field of view means the camera cannot accept only a narrow central beam. It must receive light spread across a broad image area. The camera entrance is therefore not a small hole behind the telescope. It is a large optical gateway designed to admit a wide, corrected image while maintaining careful control over focus, cleanliness, and internal conditions. In ordinary photography, the front of a camera may be easy to imagine as a lens and a shutter. In Rubin, the front optical region is much larger and more exacting because the image itself is far wider and the scientific demands are far greater. At this stage, the light must be protected from contamination. Dust, moisture, and tiny changes in the air could damage image quality if they were allowed to gather freely inside the camera. The entrance region therefore acts as a boundary. It allows light to pass while helping preserve the sealed and controlled optical environment within. This matters because faint astronomy depends on consistency. A little dust can scatter light. A small temperature change can alter focus. An unstable internal environment can reduce the value of a survey that depends on comparing images taken years apart. The camera entrance is therefore not passive glass placed in the light path. It is part of the discipline that keeps the optical system stable. The front optical elements of the camera also continue the work of shaping the image. Rubin's camera includes large lenses, and these lenses help deliver the corrected beam to the proper focal surface. Mirrors alone do not complete the job. The camera's internal optical elements refine the light further so that the wide field remains usable across its full extent. This is important because a survey of the sky depends not only on collecting light, but on treating different parts of the image with equal care. A star near the edge of the field should not become badly distorted simply because it arrives off-center. The camera entrance region therefore belongs to a larger optical partnership between mirrors and lenses. The filters are central to this region. A filter in astronomy is an optical element that transmits only a selected band of wavelengths while blocking others. In simpler terms, it allows a chosen range of color to pass through while stopping much of the rest. This does not mean only visible color in the human sense. It means a controlled band of light used for measurement. Rubin observes through several broad bands, extending from the near ultraviolet part of the visible range through the optical and into the near infrared. By separating the light into these bands, the observatory can measure not only how bright an object is, but how that brightness is distributed across different wavelengths. This is scientifically powerful because objects that may look similar in one band often differ clearly across several. A young hot star tends to appear brighter in bluer bands. An older stellar population in a galaxy may stand out more strongly in redder bands. Dust can dim and redden light in measurable ways. A distant galaxy whose light has been stretched by cosmic expansion can show a different color pattern than a nearer one. Filters therefore turn a single image into a richer observation. They allow the sky to be measured in layers of light rather than as one undivided brightness. Rubin's filter system must work on a very large physical scale because the image itself is large. The filters are among the largest ever built for astronomy, and they must remain optically uniform across their surfaces. If one part of a filter transmitted light differently from another part, the survey would introduce unwanted patterns into the data. Uniformity matters deeply because Rubin's aim is not a single dramatic picture. It is a long and consistent record of measurement. A filter must therefore behave the same way night after night and across its full area. Its scientific value depends on steadiness. The observatory does not use all filters at once. Instead, the camera system can select among different filters so that the same region of sky may be observed in different bands at different times. This creates a more complete account of celestial objects. A star, galaxy, or asteroid is not fully described by position alone. It also has a brightness pattern across wavelength. By returning to the sky in multiple filters, Rubin builds a broader visual and physical portrait of the changing and layered universe it surveys. The filter system is therefore a method of asking light to reveal more of its character. Filter changes must also fit the survey rhythm. Because Rubin revisits fields repeatedly and works through a long observing program, the choice of filter must support efficient nightly operation. The system is not designed for constant human adjustment at the scale of ordinary instruments. It is built into the camera structure as part of the observatory's larger working cadence. Filters are selected according to observing conditions, scientific priorities, and the broader plan of the survey. This gives the filter system an operational role as well as an optical one. It is one of the ways the observatory chooses how to interpret the arriving sky. The camera entrance and filters together therefore mark a subtle transition. Before this point, the telescope's task is to gather and focus light from a broad field. At this point, the light is sorted and controlled. The observatory begins to ask not only where the light comes from, but what kind of light it is. This adds meaning without altering the sky itself. The stars, galaxies, and moving bodies remain what they are. The filter system simply lets different parts of their emission be measured in a disciplined way. There is a quiet beauty in this region of the instrument. Light that has travelled through cosmic distance, across the atmosphere, and through the telescope now passes through selected optical bands before continuing inward. It enters a sealed and ordered space. It is preserved from dust and disturbance. It is refined by the camera's front optics. It is separated into measured channels of wavelength. In this way, the camera entrance and filter system act as a threshold between collected light and classified light. So this inward region is the camera's front boundary and its system of color selection. It receives the wide field prepared by the mirrors, protects the image within a controlled optical environment, and divides the incoming light into scientifically useful bands. Here, the sky is no longer only focused, it is also sorted, made ready for deeper recording with information about color as well as brightness. Beyond the camera entrance and the filters lies the recording surface itself, the deepest physical point in the path of light within Rubin Observatory. This is the sensor mosaic, the vast array of detectors where the incoming image is finally converted into a measurable electronic signal. Up to this stage, the observatory has gathered light, corrected it, protected it, and sorted it by wavelength. Here, that light is no longer simply travelling through optical space. It is received. It produces a response in matter. The image becomes data. A detector in astronomy serves a role similar in principle to the light-sensitive surface in ordinary digital photography, but on a far larger and more exacting scale. Rubin's camera contains a mosaic of charge-coupled devices, often called CCDs. A charge-coupled device is a silicon-based sensor that converts arriving photons into electrical charge. When light strikes the silicon, it can free electrons, and the number of freed electrons is related to the amount of light that arrives. In this way, brightness is turned into a countable signal. Each small element of the detector records a tiny part of the full image. Together, many millions of these elements form a detailed digital map of the sky. Rubin's sensor mosaic is extraordinary in size. It contains a total of 3,200 megapixels, spread across a large focal plane composed of many individual detectors arranged in a carefully planned pattern. This makes it the largest digital camera ever built for astronomy. The phrase digital camera may sound familiar and almost ordinary, yet here it describes an instrument on a completely different scale from everyday devices. The goal is not personal imaging or artistic capture. The goal is to record a very wide and scientifically exact image of the sky, with enough resolution to preserve fine detail across an immense field. The mosaic arrangement matters because no single detector piece of practical size can cover the entire focal surface needed for Rubin's wide-field image. Instead, many sensors are placed together edge to edge in a coordinated grid. This produces a recording surface broad enough to match the image delivered by the telescope optics. The joins between detectors must be carefully controlled and calibrated, because the survey depends on treating the whole image as one coherent field rather than as disconnected tiles. The mosaic is therefore not only a collection of parts, it is a single working surface assembled from many precise elements. Each detector contains pixels, meaning the tiny individual picture elements that sample the incoming image. A pixel does not know whether it is recording a star, a galaxy, a dust lane, or the glow of the sky background. It only records how much light falls on that small area during the exposure. Meaning comes later through analysis. At the detector level, the work is simple and exact. Light arrives, charge builds. After the exposure, that stored charge is read out and translated into numbers. The image is thus not captured as a smooth continuous sheet, but as a vast ordered field of measured brightness values. Pixel size is chosen with care. If pixels are too large, fine detail is lost because the image is sampled too coarsely. If they are too small, the system can become inefficient, noisy, or unnecessarily difficult to read out quickly. Rubin's detector design balances these concerns so that the sky image delivered by the optics is sampled with useful fidelity under real atmospheric conditions. This reflects an important truth about astronomy. A detector is not designed in isolation. It must be matched to the optics, the atmosphere, and the scientific aims of the survey. The sensor mosaic is therefore the meeting point of many decisions made farther out in the observatory. Temperature control is crucial in this region. Silicon detectors do not respond only to external light. If they are warm enough, they can also generate unwanted signal internally through thermal activity. This is called dark current, meaning a background electronic charge produced even in the absence of light. To reduce this effect, Rubin's sensors are kept very cold. Cooling helps preserve faint astronomical measurements by lowering the noise that would otherwise compete with the incoming sky signal. The mosaic therefore works inside a carefully controlled thermal environment. Its great sensitivity depends not only on its size and resolution, but on its low operating temperature. Readout speed also matters because Rubin is a survey instrument with a steady rhythm of observation. After each exposure, the stored charge in the detectors must be transferred and converted into digital values quickly enough that the telescope can continue its observing sequence without long delays. This makes the sensor mosaic an active participant in the survey's nightly cadence. It cannot simply be sensitive, it must also be efficient. The balance between low noise, high resolution, and rapid readout is one of the reasons such a camera is difficult to build. The recording surface must serve both image quality and operational tempo. Uniformity is another quiet requirement. If one detector responded differently from another, or if the sensitivity changed unpredictably across the mosaic, The survey would inherit false patterns that do not belong to the sky. Calibration is therefore essential. The observatory must measure how each sensor behaves and correct for small differences so that the final image represents celestial light rather than detector irregularity. This again shows that the mosaic is not only hardware. It is a measured and maintained system whose reliability depends on continuous understanding of its own behavior. At this depth of the instrument, the transformation of light becomes most literal. A photon that may have left a distant galaxy millions or billions of years ago travelled across expanding space, crossed Earth's atmosphere, reflected from 3 mirrors, passed through large lenses and a selected filter, now ends its journey inside silicon. There it contributes to an electrical trace. Many such traces together become an image. Many images together become a survey record. The sensor mosaic is therefore the point where cosmic travel is converted into human knowledge through matter, temperature, electronics, and measurement. This recording surface also defines the character of Rubin's imagery. Because the field is so wide and the resolution so high, a single exposure can contain stars of the Milky Way, glowing clouds of gas, distant galaxies, and moving solar system bodies all at once. The sensor mosaic receives this mixed reality without preference. It records the crowded and layered sky as one measured scene. Later stages of processing may separate the parts, but at the moment of capture they arrive together on the same silicon landscape. So this inward region is the observatory's deepest receiver, the vast detector mosaic at the heart of the camera. Here, focused and filtered light becomes stored electrical charge, then numerical image data. The outer sky is translated into a digital form without losing the broad richness of the field. In this region, Rubin's promise becomes tangible in its most direct way. The universe impresses itself onto a precisely ordered surface, and the night is turned into recordable information. The deepest physical act of recording has now taken place, but the observatory's purpose is not fulfilled by one image alone. Rubin Observatory is built around repetition. This is the next inward region of the subject. Not a material layer like mirror or sensor, but a working layer of time. The survey gains its real power from returning to the sky again and again under a planned rhythm that stretches across nights, seasons, and years. A single image can reveal an object. Repeated imaging can reveal behavior, persistence, rarity, motion, and change. In this sense, the survey rhythm is the observatory's method of turning sight into a long record. This program is called the Legacy Survey of Space and Time. Its name reflects the observatory's central idea. The sky is not only a place filled with objects spread across space, it is also a scene that unfolds through time. A survey that covers broad areas only once would create a deep map. But it would miss much of the sky's changing life. A survey that returns often but sees too little area would catch events without placing them in a larger structure. Rubin's rhythm joins these aims. It observes widely, and it returns often enough that the sky can be watched as well as mapped. The cadence of observation, meaning the pattern and timing of repeated visits, is therefore one of the observatory's most important scientific tools. Cadence determines how often a given field is seen, in which filters it is observed, under what conditions it is revisited, and how changes can be measured. It is not chosen casually. A survey cadence must balance many goals at once. It must allow broad sky coverage. It must revisit fields often enough to detect moving objects and changing brightness. It must gather enough depth over years to reveal faint sources. It must also adapt to weather, season, and the shifting visibility of the sky through the year. During a clear night, the telescope does not stare fixedly at one place. It follows an observing plan that moves from field to field across the accessible sky. Each visit is relatively brief. That brevity matters. Shorter visits allow many fields to be covered in a single night, and the accumulation of many visits over time builds both temporal coverage and deeper combined images. A single exposure may record a useful snapshot. Many repeated exposures of the same region, taken across different nights and conditions, create a much richer account. The survey rhythm is therefore cumulative. It does not rely on one perfect night. It grows through return. Across several nights, the observatory can cover the visible southern sky in a broad sweep. Then it begins again. This repeated return is one of the central qualities that sets Rubin apart. Much of the sky will be revisited on timescales short enough to trace motion and variability. Yet the same fields will also accumulate over a decade into a record of extraordinary depth. A region first seen as one exposure becomes later a sequence. Then it becomes a history. Finally, it becomes a layered archive of many observations, each linked to the same patch of sky. This rhythm also respects the sky's own structure. Not every region is equally observable at every time of year. Earth's orbit around the Sun changes the nighttime view through the seasons. A field that is high and well placed in one part of the year may be near the Sun or below the night horizon in another. The survey therefore works with seasonal accessibility. Over the course of a year, different parts of the southern sky come into better observing position. Over the course of many years, the accumulated pattern fills out. The rhythm of Rubin's survey is thus tied both to the observatory's schedule and to Earth's motion through space. Moonlight plays a role as well. A bright moon raises the sky background, making it harder to detect the faintest sources in some wavelengths and under some conditions. Survey planning must therefore consider lunar phase and position. Some observations are better suited to darker parts of the month. Others can proceed under brighter conditions with less loss. The nightly rhythm is not simply mechanical. It is responsive to the natural brightness of the sky, to atmospheric steadiness, and to the scientific value of different fields at different moments. Over 10 years, the effect of this cadence becomes profound. The same stars are measured many times. The same galaxies are revisited under different conditions and in different filters. The same regions are searched repeatedly for new transient events and for small bodies crossing the field. Noise can be reduced by combining observations. Rare events can be placed in context. Subtle long-term changes can emerge from comparison. A single observation says what appears at one time. A decade of repeated observation says what endures, what moves, what varies, and what briefly enters the field before disappearing again. The survey rhythm also creates fairness across the sky. Rather than concentrating all attention on a small set of celebrated targets, Rubin distributes observation according to a broad survey plan. This gives lesser-known regions scientific value equal to more famous ones. A faint outer field, a crowded stellar region, and a galaxy-rich deep field all become part of the same repeated program. The observatory does not wait for drama before it looks. It looks steadily, and in doing so it makes discovery more likely precisely because it does not rely only on prior expectation. There is a practical elegance in this method. The telescope's wide field, the camera's vast detector mosaic, and the observatory's site conditions all exist to support a rhythm of return. Hardware alone would mean little without this schedule in time. The repeated survey is what makes the instrument more than a powerful camera. it makes it a systematic watcher of the sky. Time is built into the science at the same level as optics and mechanics. The observatory is therefore not only a place that takes images, it is a place that measures recurrence. For astronomy, this repeated rhythm changes the kind of questions that can be answered. With enough returns, the sky ceases to be merely a catalogue of positions and brightnesses. It becomes a record of trajectories, cycles, sudden appearances, gradual drifts, and long accumulation. Small bodies can be traced. Variable stars can be characterized. Deep combined views can emerge from many visits. The survey rhythm weaves these possibilities together without needing a separate observatory for each one. One cadence serves many layers of science because it joins space and time in a single observing practice. So this region of the inward path is the observatory's temporal structure, the repeated cadence by which the same sky is seen again and again over a decade. Here, the meaning of Rubin becomes clearer. The sky is not captured once and finished. It is revisited patiently until a sequence of images becomes a living record. In this rhythm, repeated looking is not repetition for its own sake. It is the method by which the survey turns fleeting nights into enduring knowledge. After the sky has been revisited and its images gathered into a repeated rhythm, the observatory reaches another inner layer of work. This layer is the alert stream, the near real-time system that watches for change by comparing what has just been seen with what was seen before. At this stage, the observatory is no longer concerned only with taking images, or even with returning to the same field over time. It begins to react. A new exposure arrives from the camera, and the system asks whether anything in that field is different from the earlier record closely enough, clearly enough, and quickly enough to matter. The alert stream is therefore the observatory's immediate response to a changing sky. In astronomy, an alert is a machine-readable notice that something in the sky appears to have changed, moved, brightened, faded, or newly appeared. It is not a declaration of final truth. It is an informed signal based on rapid analysis. The purpose of an alert is speed joined to evidence. If a star flares, a supernova begins to rise, an asteroid shifts position, or a transient source appears where none was seen before. The alert system is meant to recognize this quickly and communicate it while the event is still fresh. In that way, the survey does not merely store the sky after the fact, it participates in living observation. This process begins the moment a new image is read out from the camera and transferred into the processing system. The raw image contains everything the camera saw in that exposure, including celestial sources, background glow, detector characteristics, and the effects of the atmosphere at that moment. Before any alert can be trusted, the image must be calibrated, meaning corrected for known instrumental and observational effects so that it can be compared fairly with earlier observations. Calibration removes part of the observatory from the picture, allowing the sky itself to stand out more clearly. Once the image has been prepared, it is compared with a reference image of the same part of the sky. A reference image is a previously built representation of that field, made from earlier observations and intended to show what is normally there. The new image and the reference are aligned carefully so that stars and galaxies match in position. Their brightness patterns are adjusted to account for observational differences. Then the system performs what is called image subtraction, meaning that the reference image is subtracted from the new one. If nothing has changed, much of the stable sky is reduced or cancelled. What remains are the differences. This difference image is one of the alert stream's most powerful tools. It transforms a crowded sky into a simpler map of change. A constant star largely disappears. A stable galaxy largely disappears. What stands out are sources that have brightened, faded, moved, or emerged. A new point of light can appear as a clear residual signal. A moving object can reveal itself by changing position between visits. A variable source can leave a measurable trace of increase or decline. In this way, subtraction does not create new sky. It clears away the expected sky so that the unexpected can be found more efficiently. The system must work quickly because the scientific value of some events depends on speed. A supernova in its earliest rise can provide especially useful information if other telescopes begin observing it soon after detection. A potentially interesting moving object may need rapid follow-up to refine its orbit. A rare transient event may fade within hours or days. Rubin's alert stream is therefore designed to operate on a short timescale, turning new exposures into alerts in about 1 minute. This is not merely a technical achievement. It is a way of making a wide survey responsive to the present tense of the sky. Not every difference becomes a true celestial alert. Some apparent changes are caused by cosmic rays striking the detector, by imperfections in the subtraction process, by unusual atmospheric effects, or by scattered light and instrumental artifacts. The alert system must therefore judge whether a signal is likely to be real. It uses measurements of shape, brightness, position, past behavior, and surrounding context to help distinguish credible astrophysical change from false appearances. Even so, the alert stream remains provisional by nature. It is meant to be rapid and informative, not final and infallible. Each alert carries more than a simple message that something happened. It includes contextual information about the detected source and its surroundings. This may include the measured position, brightness, the nature of the change, and associations with previous detections in the same area. The aim is to make the alert useful not only as an announcement, but as a packet of evidence that other systems and researchers can interpret quickly. In modern astronomy, this machine-readable structure matters because the volume of alerts can be immense. A human being cannot inspect everything first by eye. The alert stream must speak in a form that other automated tools can also understand. That scale is one of Rubin's defining features, because the observatory surveys such a large area so repeatedly and so deeply, it is expected to produce an enormous number of alerts over the course of regular operations. Many will concern known classes of changing objects such as variable stars, active galactic nuclei, supernovae, and moving solar system bodies. Some will point toward rarer events. The power of the system lies not in promising that every alert is extraordinary, but in ensuring that the changing sky is monitored broadly enough that extraordinary events can emerge from within ordinary variation. This alert stream also changes the relationship between Rubin Observatory and the wider astronomical community. A survey of this kind does not keep all urgent change to itself. Instead, it acts as a discoverer and broadcaster. It sees a wide field, detects differences quickly, and releases alerts so that others can respond. In this sense, the alert stream turns Rubin into a trigger for further observation across the world. A change first seen in a Rubin image can prompt follow-up in other wavelengths, with other telescopes, under other observing strategies. The survey becomes part of a connected observing ecosystem. Yet the heart of the alert stream remains simple. A new image arrives. It is prepared. It is compared to what came before. The stable sky is suppressed. Change is measured. A notice is sent if the signal appears significant enough. This cycle repeats through the night as new fields are observed and new images enter the system. The observatory's repeated cadence thus flows directly into a repeated act of recognition. The sky changes, and the system is built to notice. So this inward region is the observatory's immediate analytical pulse, the stream of rapid alerts that arises when fresh observations are compared against the earlier sky. Here, repetition becomes reaction. The survey does not merely accumulate images, it identifies difference while the night is still unfolding. In the alert stream, Rubin turns a changing universe into timely awareness, allowing transient light and moving bodies to stand out against the vast stability of the stars. At the deepest inner level of Rubin Observatory, the work is no longer carried by mirrors, filters, sensors, or rapid alerts alone. It settles into record. This final region is the archive and the scientific meaning that grows from it, the long-lived informational core where repeated images of the sky become a durable description of the universe. An observatory can see, record, and react, but its deepest contribution comes when those acts are preserved in a form that can be revisited, compared, measured, and understood across years. Rubin's archive is therefore not a storage room at the end of the process. It is the final scientific body of the survey. An archive in astronomy is more than a collection of pictures. It is an organized system of images, measurements, calibrations, catalogues, and relationships between observations. Each exposure must remain connected to the time it was taken, the filter used, the observing conditions, the part of the sky it covers, and the processing steps that turn raw detector output into usable scientific data. Without this structure, a great survey would become a disorderly pile of records. With it, the survey becomes a coherent map of the sky through time. The archive gives lasting form to all the observatory's repeated nights. Catalogues are one of the archive's most important products. A catalogue is a structured list of detected objects and their measured properties. These properties may include position, brightness, color, shape, motion, and variability across repeated observations. In a single image, a star or galaxy is just part of a scene. In a catalogue, that same source becomes a measurable entry that can be compared with other entries and with its own past observations. The catalogue therefore translates images into an ordered account of the sky's contents. It does not replace the images, but it allows the sky to be studied in a more systematic and expansive way. This matters because the scale of Rubin's survey is so great that no human eye could interpret it directly in full. The observatory is expected to produce tens of billions of detected objects and many trillions of measurements over its 10-year survey. Such abundance does not diminish meaning. It changes the form in which meaning must be found. Science at this scale depends on searchable records, calibrated measurements, and well-defined data products that allow patterns to be discovered across vast populations. The archive is the condition that makes such large-scale understanding possible. The scientific meaning of this record begins with the fact that Rubin joins multiple kinds of astronomy in one survey. It measures the structure of the Milky Way through huge numbers of stars, their positions, colors, and changes across time. It follows the changing sky through transient events, variable stars, and shifting small bodies in the solar system. It builds deep accumulated images of distant galaxies across enormous sky areas. It traces moving asteroids and other minor bodies with repeated measurements of position. These are not separate observatories working in parallel. They are different meanings extracted from one long and repeated visual record. Dark matter enters this archive through structure and motion. Rubin does not see dark matter directly because dark matter does not emit visible light in the way stars and gas do. What Rubin can record is the luminous matter whose arrangement and behavior reveal the gravitational influence of unseen mass, the shapes and distributions of galaxies, the clustering of matter on large scales, the motions of stars in the Milky Way, and the subtle distortions caused by weak gravitational lensing all become measurable when the sky is recorded deeply and broadly enough. Weak gravitational lensing means tiny changes in the apparent shapes of distant galaxies caused by gravity bending light along the way. Rubin's wide and repeated images will provide one of the great observational records used to study these effects. Dark energy enters by a related but broader path. The large-scale distribution of galaxies and the way cosmic structure grows over time carry information about the expansion history of the universe. Rubin's survey, especially when combined with other measurements, will help constrain that history by mapping immense populations of distant galaxies and transient events across a broad span of cosmic time. The archive thus becomes part of a deeper question about why the expansion of the universe behaves as it does. Again, Rubin does not answer such questions by direct proclamation. It contributes disciplined evidence at remarkable scale. The Milky Way gains new meaning in the archive as well. A star field that seems crowded and confusing in a single image can become ordered when positions, colors, brightness changes, and motions are measured across years. Stellar streams, halo populations, variable stars, and faint outer structures can emerge from the accumulated data. The archive allows the home galaxy to be studied not as a static band of light, but as a populated and evolving system with structure at many scales. Rubin's contribution here lies in both breadth and repetition. The same database that serves cosmology also serves galactic archaeology. The effort to reconstruct the formation history of the Milky Way from the stars and structures that remain, yet the solar system too, becomes more fully known through this long record. A moving point in one exposure may become an orbit after repeated detections. A faint outer body may be recovered across years and linked into a path that reveals its place in the distant solar system. The archive is where these scattered appearances become continuity. It preserves not only what crosses the field at one moment, but how that crossing fits into a larger physical history. There is also a shared dimension to Rubin's archive. Modern astronomy advances not only through observation, but through access. A survey of this size is valuable because it can be used by many researchers for many purposes, including questions not fully anticipated when the observatory begins its work. The archive therefore supports discovery beyond the immediate aims of the nightly schedule. It becomes a scientific commons, a long-lived public structure of measured sky from which new studies can continue to emerge. In this final inward region, the observatory becomes quieter and deeper at once. The movement of the telescope, the arrival of light, the quick notice of alerts, and the repeated rhythm of observing all settle into a persistent record. The archive is where the changing night becomes a form of memory. It is where fleeting photons are turned into a stable inheritance of data and meaning. Rubin Observatory may reveal a sky never truly seen because it will not only look at that sky with unusual breadth and depth, it will preserve the results in a way that allows the universe to be studied as one connected record across space, time, motion, and change. Night settles more gently once the work of the observatory is complete in thought. Far above the mountain, the southern sky remains what it has always been, layered with near stars, remote galaxies, dark dust, and slow movement. The atmosphere still shifts, the summit still holds its silence. Inside the enclosure, the instrument waits in balance, mirrors receive light, filters sort it, silicon records it. Time returns the same fields again and again. Differences rise into notice, records gather into memory. What begins as faint light crossing darkness becomes part of a patient human effort to understand what is present above Earth. The deeper calm of this story lies in its steadiness. Nothing in the observatory changes the sky itself. It does not command the stars or hurry the galaxies. It only watches with unusual discipline. It returns, compares, stores, and learns. That repeated attention reveals that the night is fuller than it first appears. It contains not only bright familiar stars, but crowded depths of distant structure and a constant, quiet life of change. On Cerro Pachon, the mountain, air, machine, and archive meet in one long practice of looking. Outward lies the sky in all its depth. Inward lies the record that gradually forms from it. Between the two stands the observatory, calm and exact, turning passing nights into enduring knowledge. The work is immense, yet its motion is gentle. It depends on darkness, patience, and the slow faith that repeated seeing can bring hidden structure into view. So the sky remains overhead, not as a finished picture, but as a living field that can be revisited without end. Rubin Observatory enters that field with care. It gathers its light, keeps its changes, and leaves behind a record broad enough to outlast the moment of observation. In that way, the night becomes both deeper and quieter, a place where distance, time, and steady attention meet.